let's look inside the hidden space where AI stores knowledge as we continue with the playlist on the mathematics of artificial intelligence. Inside the hidden space where AI stores knowledge. Now, here we'll be looking at topics like latent spaces, embedding geometry, high dimensional representations, and we'll see applications in areas like ChatGPT memory, retrieval augmented generation, which we've been talking about from previous videos, image generation, semantic search, and of course, recommendation systems. So first off, modern AI systems do not store knowledge like a database containing explicit facts, right? Instead, they learn a hidden mathematical representation called a latent space. So I remember in physics we talked about latent heat and things like that. Latent heat is that heat that you don't feel, but it is actually there. Like the heat required to melt ice into liquid, right? To melt solid ice into, I mean, solid water into liquid water, something like that. So instead, they learn a hidden mathematical representation called the latent space. A latent space then is a geometric world where concepts, meanings, images, and relationships are represented as points in a high dimensional space. Don't forget from previous videos, we already established that computers, machines do not understand human language, but then the way we are able to make them understand human language is to assign dimensions, vectors to each sentence, each word, each token, right? And then the computer can then understand that. So much of modern AI can be understood as, first of all, the raw data, which can be like our human language, and then that is translated to something in latent space. That's where the whole embedding and everything comes in. And then we have reasoning stroke generation. That is a kind of overview of what modern AI looks like. Now we go ahead. Don't forget, we're talking about inside the hidden space where AI stores knowledge. First off, I mean, you've seen the word latent space within this very short time a lot. So simply, you can agree with me. I mean, you should just know upfront that hidden space is called latent space, that hidden space where AI stores stuff. So a latent space is a compressed numerical representation of data learned by a model. So it is a compressed numerical representation. So having converted raw data into vectors, into dimensions like that. So having embedded it, like we've been saying, then you can then store that as numerical representation uh, by with your model. So instead of storing something like the cat sits on the mat, the neural network converts it into something like 0.31 minus 0.8 for 1.27, 0.009, and so on and so forth. And we've also established that it is not humans that do this. The model itself does this by looking at the available documents to it. So this vector becomes a location inside a hidden mathematical space. So the model learns how to organize this space so that similar things occupy nearby locations. So it is more like you are you are allocating plots of land to people and you want to put family members close by, something like that. So the intuition here is that we have a map of meaning. So first of all, think about a geographical map, and every city has coordinates, like say Tokyo, Paris, New York. Similarly, in latent space, cat, dog, lion, tiger all have coordinates instead of just direct cat, dog, lion, and tiger like that. So the closer points are, the more similar their meanings tend to be. So distance in latent space often then corresponds to semantic similarity, how the kind of meaning they have, the context in which they all play determines how close together you find them. So imagine a simple toy latent space. Suppose we represent animals using two dimensions. So the dimensions are their friendliness and their wildness. So if you talk about dog is like zero point 0.9 friendly and zero point 0.1 wild. Then we can say cat is zero point 0.8 friendly and zero point 0.2 wild. Lion is zero point 0.1 friendly and zero point 0.9 wild. While tiger is zero point 0.0 friendly and 1.0 wild. So now you have chosen numbers to represent each of these animals. So and then the closer together these numbers are, the closer together the actual animals would be. So in this simplified world, now you see that dogs and cats behave closely together, while lions and tigers are close together also. Then dogs and lions, of course, are far apart. So Dogs are so friendly, but lions are just a little bit friendly. So real models use hundreds of thousands of dimensions like this. So, we've used friendly, wild, and all of that, but we could actually continue like that. Real models actually use hundreds of thousands of such dimensions like this. Now, 7.2, why AI uses latent spaces then? So raw data can be enormous. So for instance, a 1024 by 1024 RGB image contains 1024 by 1024 times 3. So, and that is equal to 3,145,728 numbers like that. So processing millions of values directly can be expensive. So instead, what we do is we have the image, we use an encoder, and we have a latent vector. So, I mean, this will look more like the embedding kind of thing we're talking about, right? So, image encoded, then we have it in a latent vector. Then you can then decode it and, of course, generate the image. So, the latent vector is much smaller while retaining important information. So, this compression makes learning and generation feasible. So imagine a compression example here. Suppose an image contains fur, whiskers, eyes, ears. So instead of storing every pixel, the model learns a compact representation encoding these important features. So the latent space captures shape, texture, color, structure, while discarding irrelevant details. And then we have 7.3 embeddings. Coordinates in latent space. We've talked about this a lot. So an embedding is simply the numerical coordinates of an object in latent space. So now you have a clearer definition for embedding. So an embedding is simply the numerical coordinates of an object in latent space. Or you can say that an embedding is a numerical representation of an object in latent space. So examples, you can have king to be 1.3, 0.4, and so on. Queen is 1.1, 1.0, and so on. Man is 0.8, 0.2, and so on, while woman is 0.6, 0.8, and so on. So the actual numbers have little meaning individually, but what matters is the geometric relationship between the vectors. So we've seen things like cosine similarity. I think you're still going to see that here. So we then see that meaning comes from geometry. So the important fact is not that king is 1.3 and 0.4 as we have there. Instead, king is close to queen because 1.3 in the first dimension, king is 1.3, queen is 1.1. In the second dimension, king is 0.4, queen is 1.0. So um so compared to others, they may not be that close. So instead, we see that king is close to queen. King is far from banana. Then king and queen share many properties. So meaning emerges from relative positions in space. So we derive meaning from the proximity of objects in space, proximity of the embeddings in space. So neural networks learn geometry rather than symbolic rules. So we're talking about geometry of meaning now. So neural networks learn geometry rather than symbolic rules. So instead of storing if an animal then blah blah blah, they learn animals occupy nearby regions. The model creates neighborhoods of meaning. So imagine semantic clusters now, where have things like this now. A learned latent space may contain clusters like animals, say dog, cat, wolf, and fox, vehicles like car, truck, and motorcycle, foods like pizza, burger, sandwich. So the clustering emerges automatically during training. So that's why that it's the job of the model that is being used to do the whole clustering, the grouping together of things that have similar meaning or things that appear in similar contexts. So, for example, you can have distance between embeddings. Yeah, suppose dog is 0.9, 0.8, cat is 0.8, 0.9, and car is minus 0.7, minus 0.8. The Euclidean distance between dog and cat, for dog and cat, now that's 0.9 minus 0.8 squared. That's 0.1 squared, which is 0.01. Then 0.8 minus 0.9, that's minus 0.1. If you square that, you still get 0.01. So that'll be square root of 0.02, and that is 0.141. This is very small in terms of distance. So dog and cat are much far apart. So if you look at dog and cat now, they are much far apart. So small distance usually implies similar meaning. So it means they are really that close by. So if you do what we've just done here now, if you just do this, you see for dog and cat, you have 0.141, and for dog cat, you have 2.262, like that. So then let's talk about similarity measures. We considered that in the last video too. So never mind that this repetition, we have to repeat this concept so that they can really like they can be established in your thinking. So similarity measures now. Two common similarity measures are Euclidean distance and cosine similarity, and both compare embeddings geometrically. So for Euclidean distance, for vectors x and y, the distance between x and y is the square root of summation from I equals 1 to n of xi minus yi squared. And interpretation is that small distance means the objects are similar, while large distance means the objects are different. So Euclidean distance measures physical separation in space. So here it talks about physical separation in space. On the other hand, we have cosine similarity, which measures the angle between vectors. So cos theta is x dot y over modulus x times modulus y. The interpretation is that if the cosine similarity is one, we have identical direction. So it means that the vectors they are facing the same direction. If it is zero, it means the vectors are unrelated. That is, they are inclined at angle 90 degrees. They are perpendicular. Okay. Then if it's minus one, you have opposite direction. So most language embedding systems use cosine similarity because they show direction rather than just distance apart. Now, using cosine similarity, now you have x is 1, 2, 3, y is 1.1, 2.1, 2.9. So if you compute the cosine similarity of this by saying 1 times 1.1 plus 2 times 2.1 plus 3 times 2.9 all over modulus of 1, 2, 3, the modulus of 1.1, 2.1, 2.9, the cosine similarity is very close to zero, as we're going to see in the Python code. This means the vectors point in almost the same direction and therefore represent highly similar meanings. So imagine that here. So you have 1, 2, 3, 1.1, 2.1, 2.9. So if you do the whole cosine similarity thing, you get 0.99, which is close to 1. So that means that these two vectors point in the same direction. So let's talk about high dimensional spaces then. Real AI systems do not use two dimensions. So typical embedding sizes can be quite big. So if you have a model like word to vector, that's converting word to vector, right? It has 300 dimensions. So if you take a cat, now you're looking at different things so that the more details you have, the more, the clearer you can do what you need to do, trying to locate them around other objects that are similar. So for BERT, 768, for GPT embeddings, you have 15,000, 1,536 plus dimension. That's a lot. So the more the dimension is, seems the better the result. For clip, now it can range anything from 512 to 409. 4096. So every dimension captures some aspect of meaning. Just like we had before, we looked at animals and how friendly they might be and how wild they might be. So, and then you can just continue like that. Maybe color, texture, fur, and things like that. You just keep going, and the more dimensions you have, the better the results you get. So now the question is, why many dimensions though? Now, we need so many dimensions for objects, so for machines to understand, because meaning can be quite complex, because a word may contain information about topic, sentiment, formality, gender, context, style, domain knowledge. One dimension cannot represent all these features. So high dimensional spaces allow many independent semantic directions. So now we then have the idea of the curse of dimensionality. So as dimensions increase, visualization becomes difficult for sure. Human intuition then fails, distances behave differently, yet neural networks are surprisingly effective in these spaces. So when we have very large dimensions, it's really difficult for humans to understand. And that's where machine we need a collaboration, a human computer kind of interaction, for things to get better. So, machines cannot understand our language, but by putting our language into their language, into vectors, they can understand. And in fact, in that dimension, in that domain, the humans find it difficult, but machines can do a better job. And then we partner together like that, we get things better. So, neural networks are surprisingly effective in these spaces. Modern AI relies heavily on high dimensional geometry. An example is distance growth. Now, if you consider random vectors, as dimensions increase, distances tend to grow. This is a fundamental property of high dimensional spaces. So imagine for dimensions in 2, 10, 100, 1000. If you take x to be any random dimension and you take y to be another random dimension, I try to find the distance between them. So you get the dimension and the distance now. So I mean, just pairing them up, randomly. So if I do this now, if it picks two, the distance, and y picks another one randomly. So you just have should we print X and Y also? I think we should print X and Y. Um, Trying to think about that. Okay, let me just print X and Y and see what happens. Yeah, let's see if we can print all of this. Okay. Now that's even harder to read. Okay, so I think it's better just leave it this way. Okay, so if you pick randomly, so 2, you have 2.277, 10, 3.5, 100, 14.9, 1045. So the distance is growing like that. So we have distance growth going on like that. And that's one thing that contributes to the cost of dimensionality. But machines are good at handling these things. So let's talk about visualizing high dimensional embeddings. Now, humans can only directly visualize 2 dimensions or 3 dimensions. I mean, beyond 3 dimensions, things go spiritual, things go metaphysical. So, we can only handle things in 2 dimensions, like flat objects or solid objects. So, AI embeddings often have hundreds of thousands of dimensions. And then dimensionality reduction techniques help us to visualize them because we can't really see them. So, we have to bring them into our own realms. And we have methods for bringing things into our into to reduce dimensions for humans to be able to appreciate them. So common methods include things like PCA, TSNE, and UMAP. And then we have principal component analysis. So PCA finds directions that preserves as much variance as possible. Okay, so it finds directions that preserve as much variance as possible. So it gets what's really, it's more like drilling down to get what really matters in a system. So a 768 dimensional embedding can be projected into dimensions while preserving major structure. This allows visualization of clusters and relationships. Imagine if you deal with PCA here, I think under my playlist on machine learning with EJD. I did took this algorithm one after the other to demonstrate. So I showed the codes and things like that. So this is us looking at PCA here. Imagine to work with PCA, right, from scikit-learn dot decomposition, you need to import PCA, that's principal component analysis, and then import numpy as NP because you also need that for random generation like this. Imagine we have data, random data generated 100 by 50 dimensions, that is 100 rows and 50 columns, for instance. So now 50 columns, of course, 100 rows means 100 data points, but 50 columns means 50 variables. Of course, that's still manageable, but it's still a lot for humans, right? So PCA now, so to do the PCA, we just say PCA equals PCA number of components 2. We just want to reduce the number of components to 2. So if we reduce that now, we have PCA.fit transform data. And by the time we look at the shape of the reduced data, you have 100 by 2. So instead of 100 by 50, this one, so PCA can help you to drill it down to 100 by 2, like that. Then we have vector arithmetic. So one of the most famous discoveries in embedding research was the fact that king minus man plus woman is approximately queen. Okay, so relationships become directions in latent space. Of course, these are human words, right? But in vector form, we can understand the concept. Imagine the geometric interpretation, for instance, king, queen, man, woman. So the transformation is this. So man to woman is approximately the same as direction. King to queen in that case, because it's more like they operate the domains in which they operate. So then relationships like that become vectors. So imagine a Python demonstration of this. Imagine king is 5 4, man is 3 2, and then woman is 3 5, right? So we then have um queen to be king minus man plus woman. That's in the vector form, right? That's 5 plus minus 3, 2, 2 plus 3, 5. Then for this now, you have 5 minus 2, 2, 2 plus 5, 7. So if you print queen now, queen then is like 5 by 7, like that. So we have that kind of uh, vector arithmetic going on there. So let's talk about latent space inside ChatGPT. ChatGPT processes text through multiple stages. So you input your text, I mean your query, and then that query is broken down into tokens. That's maybe letters or characters or even full words, depending on what the context looks like. So the breaking down of the text is called tokens. So when you break down text, you have tokens, and that's the process of converting text into tokens is what you called tokenization. And then from tokens, now you have embeddings. Now the process of assigning vectors to each token is what you call embedding. So now with this, you transform the tokens into a vector space by the process of embedding, and then you don't have your transformer layers, and from there you can match the text with whatever you already have from the document stored in the model or which the model is trained, and then from there you can get your prediction. So every layer transforms representations into new latent spaces. So the model continuously reshapes meaning as information flows through the network. So talking about hidden states now, imagine at layer one, h sub l plus or layer L, right? H sub l plus one equals f of h of l. Okay, so that means h at this stage is actually a function of h at the previous stage, where h sub l is the current representation, while f is a length transformation. Knowledge is distributed across many layers and billions of parameters. So, like I've said from the beginning, right? AI is just doing simple things on large data sets on with billions of parameters, and then everything goes very serious. So example imputes the fact that the doctor entered the hospital, so the model may activate regions associated with medicine, healthcare, buildings, occupations, and patients. Doctor, because that's related to medicine and healthcare. Hospital is a building, right? Then of course doctor is still occupation, and then doctors attend to patients. So these concepts influence prediction of future tokens. So everything AI is doing for you is just probability, just guessing based on experience, based on the data it had been trained on. So let's talk about ChatGPT memory and embeddings. Many AI systems store memories using embeddings. So example memory, users like jazz music. That is direct text, right? So embedding vector A. So and so maybe you embed this as vector A. Then you now later query this recommend music. And then embedding vector. So this is now embedded as vector B. So the system searches for nearby vectors. So and we have a retrieval through similarity. So the memory retrieval process, you have question, you have the question is embedded, you then have a vector search, and then it associates things that look alike, and then it generates answer. This is the core idea behind retrieval augmented generation. Retrieval augmented generation. So latent space in image generation. So it has been established, right, that that space where that hidden space where AI stores information is actually the latent space, that which is a space for storing numerical representation of ideas of human language of things that humans supply to the computer. So modern image generators work primarily inside latent spaces. So examples include Stable Diffusion, Dial.e, Midjourney. They do not generate images directly pixel by pixel, right? What they simply do is they follow this pipeline. You put your image, and the image is encoded into numbers because the computer doesn't understand images, just understand the numbers the images represent, and then it is encoded and it is stored in latent space, and then it is diffusion process, and then that is decoded, and then we have an image generated for you. So the model operates on compressed representations rather than raw pixels, right? Compressed representation rather than raw pixels. Now the question is, why use latent diffusion? Instead of manipulating millions of pixels directly, like 1000 by 1024 by 1024 by 3, the model works on compact latent representation. This dramatically reduces computational cost while preserving visual quality. So, example of latent representation now. Imagine a latent vector contains catness, furriness, orange color, cartoon style. Then the vector might be 0.9, 0.8, 0.2, 0.7, 0.2. Increasing the cartoon dimension could produce a more cartoon-like image while preserving the cat like that. So we then have interpolation in latent space. Latent spaces often allow smooth transitions. Suppose A is cat and B is tiger. Moving between them gradually creates intermediate representations. So to move from cat to tiger, there's some interpolations that need to take place. So, and we have this simple linear interpolation formula. Given vectors A and B now, cat and tiger. So P now is equal to 1 minus alpha multiplied by A plus alpha plus B, where alpha lies between 0 and 1. So as alpha changes, as you keep changing this alpha, for instance, when alpha is 0, you just have A, and then B is gone. Then when alpha is 1, A is gone, and you have only B left. So as a result of that, it means that to transition from cat to tiger, so alpha has to take values from 0 to 1. So as alpha is changing from 0 to 1, you have uh, slow transitions from cat all the way down to tiger. So as alpha changes, the representation smoothly morphs from A to B. So imagine this now. You have a Python interpolation thing here. Cat is 1 0, tiger is 5 4. So for alpha in alpha space from 0 to 1, So you then have the point is 1 minus alpha multiplied by cat, this cat here, plus alpha multiplied by tiger, which is 5, 4. So for if as the alpha keeps, alpha starts from 0, so you have 1.0, and it keeps going until it gets to 1. You then have 5, 4, like that. So 1, 2, 3, 4, 5. This is what this. Okay, let me see. It looks like that's what this represents. So if we do it in 4 steps. Okay, so it gets to 5, 4 in 4 steps. So if you do it in 40 steps, so the transition is slower. So you keep going, going, going until you finally arrive at 5, 4. So the number you have after 0, 1 here is the number of steps in which you want to arrive at tiger, starting from cat. So if you do it in, let's say 10 now, uh, let's say 10. So it means in 10 steps, you keep moving gradually. So you have a transformation taking place until you progress to this point. Now, why do latent spaces work? Neural networks learn representations where similar concepts are nearby, different concepts are distant, relationships become directions, concepts form clusters, and this geometric organization makes reasoning and generation possible. So, and then we talk about the idea of manifolds. So, modern researchers often describe latent spaces as manifolds. So, a manifold is a structured lower dimensional surface embedded inside a higher dimensional space. So, a manifold is a structured lower dimensional surface that is embedded inside a higher dimensional space, which of course most of embeddings we do are very high dimensional. So manifolds then help to take care of that. So examples, you have a sphere surface, you have a torus surface, you have a semantic manifold. Real world data occupies only a tiny fraction of all possible configurations, right? So we then have natural images live on a manifold. Although an image contains millions of pixels, most pixel combinations do not correspond to real photographs. So natural images occupy a highly structured region of space. So natural networks learn this structure. Image generation can be viewed as navigating this manifold. In summary, what we've been saying so far is this, that um, modern AI can be understood as, a journey from raw data to embeddings, to latent space, to geometric relationships, to reasoning and search and generation. And then the central insight is knowledge is represented geometrically. So distance, direction, clusters, and neighborhoods inside high dimensional latent spaces become the foundation of modern AI systems. So our key takeaways from everything we've been saying is this: latent spaces are latent spaces are hidden numerical representations learned by neural networks. Embeddings are coordinates inside latent spaces. So then similar meanings tend to occupy nearby locations. High dimensional geometry enables rich semantic representations. ChatGPT processes information through evolving latent representations. Memory systems retrieve information using embedding similarity. Image generators manipulate latent vectors rather than raw pixels. Vector arithmetic reveals meaningful relationships. Interpolation allows smooth concept transitions. So, like we saw with the cat and tiger, then much of modern AI can be viewed as computation over geometric knowledge spaces. So let's see some practice problems as usual. And then, of course, I get to solve two of them. In this case, I'll be solving problems 4 and 16. Problems 4 and 16. So, so these are the first 6 questions. I'll be taking care of this. A search system retrieves document by selecting the nearest embedding vectors. Explain why embedding similarity can retrieve relevant documents even when exact words do not match. Of course, we've talked about things close to this in previous videos because meanings matter more than actual words, for sure. So these are the first 6 problems. Then from 7 to 12 now, the next 6. Okay. Then 13 to 20. Okay, we can then show the rest now. So I'll also be dealing with 16. In your own words, explain the statement, knowledge in neural networks is distributed rather than explicitly stored. So let's go ahead and deal with this problems, and then we'll be done with this. So let's start with problem 4. A search system, a search system retrieves documents by selecting the nearest embedding vectors. Explain why embedding similarity can relevant retrieve relevant documents even when exact keywords do not match. Okay, so let's go ahead and talk about the solution. So first of all, traditional keyword search, that was what was used before semantic search emerged. Traditional keyword search relies on exact word matching, word matching. For example, imagine you have a query. How do neural networks learn? So that's the query right there. How do neural networks learn? And then you already have some document where you have something like this. Deep learning models acquire patterns from data. Okay, you have a document like that. So you see that a keyword based system, a keyword based system may fail because, so if you look at the query and the document, there's no word matching exactly. But I mean, the document is answering that question, but there's no actual matching in words. So the keyword-based model may fail because, first of all, neural neural networks does not exactly appear, does not exactly appear. Then two, learn learn does not exactly appear. Learn does not exactly appear. So you see, you have neural networks here and learn, but then, okay, well, deep learning is here, but it's not the exact word like that. So, however, 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 an embedding, an embedding, an embedding model converts both the query, both the query, and so the traditional method will fail, right? So, but an embedding model converts both the query and document into vectors, that that capture meaning rather than exact wording. Okay, so the query and the document are converted into vectors that capture meaning rather than exact wording. So imagine example then. Example. If the example now is that for the query embedding, query talks about how neural networks learn. So for query embedding, imagine you have Q equals 0 0.8, 0 0.2, 0 0.7 in three dimensions like that. And then we have the document embedding. The document itself is that deep learning models acquire patterns from data. So the document embedding, query embedding, document embedding. So you have D now to be 0 0.82, 0 0.18, 0 0.75. Now, because the vectors, because the vectors are close together, as you can see, so 0 0.8, 0 0.8 to 0 0.2, 0 0.18, 0 0.7, 0 0.75. So because the vectors are close together in latent space, the system recognizes recognizes that both discuss machine learning concepts. Machine learning concepts. Therefore, 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 embedding search retrieves, embedding search retrieves documents based on semantic similarity rather than exact keyword overlap. So what's the key idea then? So key idea. So we have that embedding retrieval, embedding retrieval answers. Does this mean does this mean something similar? Does this mean something similar? Then, I mean, does this mean something similar rather than does this contain the same words? Does this contain the same words? So, and that's where it makes sense, right? Because you can have a bank, you can have river bank, and you can have bank account. So, semantic retrieval, embedding retrieval rather, helps to, you know, help us know what exactly the meaning is that we are trying to convey. So let's go to problem 16. Problem 16. So it says in your own words, explain the statement, explain the statement, knowledge in neural networks, knowledge in neural networks is distributed rather than explicitly stored. So by way of solution, then we have this in a traditional database, a traditional database. Knowledge is stored explicitly, actually. Knowledge is stored explicitly. Example, you have a fact and you have the value stored directly. So first fact, capital of France. The answer is Paris. Next, you have capital of Japan. Capital of Japan. And the answer is Tokyo. So that's in the traditional system. On the other hand, right, the information exists in clearly defined locations. So, but then neural networks work differently. So there is usually no single neuron or parameter that stores an entire fact, such as Paris is the capital of France. Okay. Instead, the fact is encoded across many weights, neurons, and layers simultaneously. So let's see a simplified view. So we have a simplified view. Fact A may depend on say weight 1, weight 204, weight 17092, weight 801231. On the other hand, fact B may share some of those weights. Fact B may share some of those weights. Knowledge is therefore distributed across the network. So when a question is asked, the network combines information from many parameters to reconstruct the answer. Example, when ChatGPT answers, when ChatGPT answers, what is the capital of France? What is the capital of France? What is the capital of France? It does not look up a database entry. Database entry. Instead, billions of learned parameters interact to produce the token Paris easily. So the answer emerges from patterns stored throughout the network. Finally, the key idea we see here is that distributed knowledge means first of all, no single location stores a complete fact that then two, many parameters cooperate to represent information. Three, knowledge emerges from collective patterns inside the network. So finally, this distributed representation, is one reason modern neural networks can generalize beyond memorized examples. And with that, we come to the end of this interesting video on latent spaces where AI stores information. Okay, so yeah, look at the practice problems again. 1 to 6 here. 1 to 6. 7 to 12. And then the rest. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not, why not go ahead and do that right away? By and also hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of this channel also by clicking on join. That gives you special privileges you'll find when you click ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.